One of man's basic needs is shelter from the natural elements. Primitive man lived in caves, and his successors started to construct buildings. Now, a key feature of the design of a building is the climate, and another important feature is the materials available locally. So the Eskimos built their homes out of ice, the igloo, and the Red Indian built his wigwam out of animal skin. Earth is a very, very common material. It's very cheap, and it's very easy with a little bit of energy to make a building out of it. In this film here, I've shown some mud huts, clay huts, very low thermal conductivity, so thick walls, small windows can keep out the heat. Timber was the dominant structural material for homes for a long, long time, from the Stone Ages to the last 2 centuries or so. It's still a very, very common, important material in the home. Earth, in the form of fired bricks or natural stone, can be used to build row upon row of terraced houses like these here. My own home in North Wales was built of granite. These homes here were very, very popular in the mid-19th century. Thousands upon thousands of Coronation Streets. The roofs, wherever the slate was available, of course, was North Wales slate, the best slate. This kind of building here is now very, very popular. It makes use of high tech, if you like. Precast concrete, steel, strengthened steel. But despite that high technology, of course, they do present us with social problems. There have been many, many innovations recently in the design of buildings and also in the structure of them. There are many, many new building materials available, plastics, new adhesives. Now, how many of you have seen these large buildings these days that are more window than wall? This is because glass has been strengthened now, and it's generally called a building material. The design of houses and homes and civil buildings has also changed. Now, the Prince of Wales, the real one, not me, has had a few words to say on that matter, and I shall stay clear of that debate. What I intend doing in this lecture is to concentrate on 3 aspects of buildings. I want to talk about the strength of buildings. I'll say something about architectural glass and the uses we can make of glass. And I'll also talk about access to buildings. One of the first things that I want to do is to talk about the location of buildings. And you see in front of me here a very nice model built by my colleagues, and they rather unkindly, I think, have called this the Roberts School of Acting. I think they want to teach me a few lessons, I think. The purpose of this model here is to try and simulate the patterns of wind, the contours of wind. So here we have a wind source, and we have various indicators of wind here. And you can see certain areas where the wind is very, very strong. Other areas, very, very still. Some of these threads are hardly moving at all. If I move this thread along here, you'll see the wind is pointing in the left direction here. As I move it along, you can see how the turbulence swings it in another direction. And over the years, people have made use of structures like this, and bigger structures. People have had large wind tunnels and larger models to try and simulate the wind effect. But modern technology has given us this computer. And with computer simulation, we can really ease things for the architect. And what I want to show you now is a sequence which is doing something very similar to what I've done here. You can see that I have a structure, a building complex. This could be a shopping complex, or it could be a housing estate. Very, very similar to the one that I have here. And what we're going to do is we're going to put in a certain wind speed. The wind speed I've selected is 2.5 meters per second. It's a fairly low wind speed, only about 6 miles per hour. And we've taken it from this southeasterly direction here. And what we're going to do is to try and work out what the wind velocity is at different positions above the ground. The color code that I'll be using, the red reflects high wind velocities, values in this case near 3 meters per second, and the blue, very, very low velocities. And with the aid of mathematics, in particular theories of fluid mechanics, we can plot out just what the wind velocity is at a certain height above the ground. And you see these lovely little vectors here. These vectors here, like the red one, indicates a speed of about 3 meters per second in this direction. But see how variable it is. Just in a corner like this, the wind velocities are extremely low. And you have the whole pattern around here, around the building complex that I've just discussed with you. And so it enables the architect now to quickly see where perhaps he should site a particular building. An alternative way of looking at this kind of simulated model is using contours, just like the weatherman does when he plots out isobars on his map. So what we're plotting out here are contours of constant velocity. So these are the very, very low velocities that you find here. These are the very, very low wind speeds. The green reflects the middle wind speed range. Some of you may be surprised to find that there are velocities here higher than the prevailing wind velocity, 2.5 meters per second. Well, the reason for that is something we call the vortex effect. You can actually have these velocities being greater than the prevailing wind velocity. So you see, when you see a lovely contour map like this, the architect can now say, well, there's considerable turbulence, let's say in this area here, where you see the velocities changing a lot. So that's the last place I'd want to put a tennis court, for example. And so that's the sort of design aid now that the architect and the structural engineer can make full use of. Wind brings havoc to even the best organized societies. And I've indicated on the film here a typical example of the damage that wind can do. You can see those poor houses there being lashed by those waves, all produced by a storm at sea. When we think of wind damage, and a spectacular one very common bit of film that you may already have seen is the Tacoma Bridge disaster. And although it's nothing to do with homes, I thought you'd like to see this lovely bridge collapsing. The Tacoma Bridge on the west coast of America had been oscillating for many, many years. But on one particular week, the wind in a particular direction found a resonant frequency in that bridge. And there it is, you can see it oscillating away, and there it is, collapsing. Another example of wind and resonance is shown on the next sequence that I'll be showing, which is to do with a steel chimney. In fact, it's an aluminium chimney, I think. And you can see it heaving away at its resonant frequency. The wind, again, has caused this object here to vibrate with that characteristic frequency. Every object will have its own natural or resonant frequency. Every building will have a resonant frequency. Those of you who are music lovers will know that in a concert hall, it makes a big difference whether you have a live hall or a dead hall. It's all to do with the shape of the hall, its volume, and the materials in it. Your house will have a resonant frequency. What I have on here is a two-story building. Well, let's pretend it's a two-story building. A building like that typically has a resonant frequency of about 10 hertz. On the other hand, if we take a large building like this, then it will have a lower resonant frequency, maybe in the range 0.5 hertz to 5 hertz. If you are living in an earthquake zone, it makes a tremendous difference just what the resonant frequency is of your home. We've seen on the television in the last week or so the terrible damage inflicted in Armenia due to an earthquake. On the film here, I've shown a photograph of a much earlier earthquake, the San Francisco earthquake in 1906. And you see the devastation there. It's as if a nuclear bomb has exploded. Tremendous devastation. Most earthquakes have their resonant frequency in the range 1 to 7 hertz. Most of the energy of the earthquake is in that frequency range. And it's very, very important, therefore, if you're living in an earthquake zone, to have a home that has a higher frequency than that band of frequencies that the earthquakes are in. What I'm going to try and do with this demonstration here is to indicate to you just what those frequencies are and the differences between the low-story buildings and the high-story buildings. We call this a shake table. And what I'm going to do is to put a certain amplitude of vibration on. You can see it shaking. And I've already positioned this very, very close to its resonant frequency. If I lower the frequency, it dies down. But if I get close to the resonant frequency, it really can start oscillating quite violently if I wanted to. And you'll see on the scale here that the frequency is about 10.5 hertz. So these low-story buildings have relatively high resonant frequencies. What I'm going to ask Bryson to do now is to replace this two-story building by this much larger one. And we'll see what the frequency is of this. What we'll find is that the frequency is much lower. And that's why tall skyscrapers like this are much more vulnerable in an earthquake zone. When people did research on the big Mexican earthquake that occurred a few years ago, they found that most of the devastation occurred in buildings with between 6 and 12 stories. The others were perfectly okay. So that the height is very important. The weight distribution is also important. And so the floors that Bryson is building here and the number he puts in will vary the resonant frequency quite a lot. So what should we do? Just put 2 or 3 more floors on, Bryson, then we can set the amplitude going again. In a building like this is the old-fashioned building that are very, very heavy beams and very narrow columns. And this is the type of building that we had in Armenia. And it really isn't a very safe structure at all, because it's very brittle at about a hinge point about there. And of course, if that breaks, the whole structure comes down. Well, let's see now just what the amplitude of vibration is. I'm going to lower it down now towards, I'm going through 8. And if I turned up the juice a little, I'm sure it would collapse very quickly. The way to prevent a building like that collapsing, or at least minimize the damage, is to have a rather different structure, like the one I've shown here, where the columns are much sturdier and the beams take much more of the strain. So that if an earthquake hits a building like this, it'll be the beams that will tend to buckle rather than these sturdy columns. So that gives you some idea, I think, of just how terrible resonance effects can be. There's a lighter side, obviously, to resonance as well. In this lecture theatre in 1828, a lecture on resonance was prepared by Wheatstone. Wheatstone is better known to you, I'm sure, for his measurements on the Wheatstone Bridge and his work on telecommunications. But Wheatstone came from a very musical family. In fact, he invented the concertina. And he prepared a lecture, a discourse, for this very lecture theatre. But Wheatstone was a lousy lecturer. He really was hopeless. And all his lectures at this lecture theatre here were given by Faraday. Another famous speaker on resonance in this lecture theatre was John Tyndall, who replaced Faraday as the director of the Royal Institution. The present one is John Thomas. He was John Tyndall. He was a very good mountaineer, and he was very cunning as well, because he arranged that his research would be on Welsh slate, and that gave him an excuse to go to North Wales whenever he wanted. I have in front of me here a very, very simple demonstration of resonance. I have some whiskey glasses, not filled with whiskey, I'm afraid, just filled with H2O. And as you can see, the heights of them vary. And what we're doing in that case is varying the resonant frequency of those glasses. And I'm sure you've done this type of thing at home. So that this empty glass has a very different frequency to the one that's full here. And so with 5 glasses like this, on my left here, you see some beautiful glass objects. Well, perhaps not quite so beautiful, but very, very functional. Milk was first put into milk bottles exactly 1 century ago. And obviously it's very, very tough glass that we have there. I've also shown some high-tech glass. This is the type of thermal insulation fiberglass that you have in your roof space. And fiber optic communications is now important. So glass in a high-tech form. Let me tell you something about the history of glass. Glazing has been mentioned in old texts 3,500 years ago. But glass in the form of separate vessels only came about 1500 BC. And it was much later than that, about the time of Alexander the Great, that we had blown glass. Early Roman records show that the Romans used windows made of glass. In the ruins of Pompeii, people have discovered large bronze frames, about 21 inches by 28 inches, clearly designed for glass. In this country, it's around the 7th century there's the first record of windows in glass, and this is really in churches. The Venerable Bede's Church in Monk Wearmouth in the northeast of England, record of that in glass. And the glass in York Minster was put in, the early glass, about that time. As far as domestic buildings are concerned, the first record of that is in the 13th century when King Henry III glazed some of his royal palace. In my last lecture, I referred to a tax on wax. The government of the day taxed candles. Well, windows were taxed as well in the late 18th century. At the same time, an excise duty was put on glass. And what this did was to drive out the glass manufacturers in this country to places where there wasn't duty, for example, Ireland. And the way the glass industry started in Ireland, producing beautiful objects like this lead crystal glass, was because of that window tax and the excise duty. This lead crystal glass is glass that contains an excess of lead oxide, and it gives it a higher refractive index, and when it's cut, you get really very, very beautiful patterns. One example of glass, a bit gruesome perhaps, is this glass eye. I don't know how many of you can see it. You can see it winking at me there. About 1827, Faraday became interested in glass. The Royal Society asked him to do some research in glass. It wasn't one of Faraday's best periods. The work wasn't very successful. But a few years later, in 1845, using the same glass as he'd had in 1827, and I have a piece of it here, this is a borosilicate glass, he discovered an effect that we now call the Faraday effect. And what I'm going to try and do is to reconstruct that experiment that he did with you here. I have a laser beam, and it's very, very safe, I assure you. There's nothing to worry about. Obviously, Faraday didn't use a laser beam. He used white light with filters. But we're going to have that laser beam pass through and hit this screen here. We have a sheet of Polaroid here, and if we switched on at the present time, we wouldn't be able to see anything. The clever thing that Faraday did was to pass his light beam through the magnetic field that I have here. And he discovered that the magnetic field would change the polarization of that beam of light. And so we're going to try and reconstruct that using one of the pieces of glass that Faraday worked with in 1845. So Bryson is going to place that in the beam now. As I say, to begin with, you won't see anything. But when Bryson switches on the magnetic field, we should see the laser light hitting the screen. And you can see there's a nice red spot there showing that the laser has been propagated all the way through. And now, if you can put off the magnetic field, there it's gone. So it's not a very dramatic effect, but it's a very, very important effect. It's important because a few years later, Maxwell, when he was formulating his laws of electromagnetism, really regarded that as a very, very crucial experiment. Well, what is glass? You've seen these numerous objects here. There are others that we use in the home, like the oven door, the screen of your television. It's used in many, many places in the home. What is glass made of? Well, glass is, common glass that is made of a silicate, silicon oxide. By mixing it with soda and lime and heating it up to about 15 or 1400 degrees centigrade, it forms a liquid. As that liquid cools at about 500 degrees centigrade, it forms a solid. In that solid form, you can then start regarding it as a material that you can cut and work with. About 30 years ago, there was really a revolution in the production of glass. And I'm referring to the float glass method pioneered by Pilkingtons. What this involves is taking the molten glass at about 500 degrees centigrade and floating it on the surface of molten tin in a special non-oxidizing atmosphere. And what this means is that the glass comes gently down onto the tin, is gradually moved along the moving belt, and cools in a very, very controlled way. It is important when you have this molten to solid stage to regard glass as being you have to be very, very careful the way you produce it and work with it. Because glass, once you've produced it, is full of internal stresses. And in making certain things like this bowl here, you need to anneal the glass afterwards and then let it slowly reduce back to room temperature. I have here a beautiful example of a cut glass. And let me show you alongside a very, very similar specimen. Although they might look the same to you, they're very, very different. The one on the right-hand side is annealed glass. As I mentioned to you, once it's been produced, it's been heated up to get rid of those internal stresses, and then it's been allowed to cool down gently. But this one is not annealed. Now, if I drop this very tiny piece of glass into there, nothing happens. Just as well. Now you watch as I drop it into this one here. The difference between annealing and not annealing. Now, having shown you how fragile glass can be, why don't I try and show you how strong glass can be? I've referred already to this milk bottle. Bryson now is going to try and carry out a controlled explosion in a milk bottle. What he's going to do, oh yes, I think I'll have my safety helmet here. A Welsh safety helmet. That's to go with my University of Wales tie that I'm wearing today. We have a protective sheet around this milk bottle just in case anything should go wrong. But what Bryson is going to do, he's going to mix oxygen and hydrogen, a very combustible mixture, and he's going to mix it inside that milk bottle, but obviously you are protected should anything go wrong. Fire. Well, I'm going to follow that somehow. It's woken you all up, so... And I'm going to try and do an even more spectacular demonstration with this 5-pound ball. You might think it's a shot put and I'm Jeff Capes or something, but regard it as a cannonball. It really is very, very heavy. Would you like to feel the weight of it? It's quite heavy, isn't it? Try. Would you like to come and help me with this experiment? What's your name?
Beatrice.
Beatrice, come on, Beatrice, and let's see if... Now, would you like to stand up on that stool? And then I'll tell you what we're going to do. You see down below here, we have what looks like a big window, don't we? And you know what I'm going to ask you to do, don't you? I'm going to ask you to throw this ball down onto that window. Now, this has been done millions of times, I assure you. Well, at least we did it in rehearsal once. What I'd like you to do is to put that ball up here and drop it in there. Right. Now let me help you down. And just in case anything should go wrong, why don't you go back to your seat? And I'll now be responsible for unleashing this huge cannonball. And it's an experiment you shouldn't try at home, by the way. Here we go. There, see? Survived. I think I'll take this off as well. Let me say now a word about not the strength of glass, but how you can start using glass usefully in the home. Those of you who live near airports or near busy railway stations or where there's lots of traffic realize how annoying sound effects can be. All the sound of that traffic. Soundproofing a house is probably more important than heat-proofing in many cases. Sound doesn't travel through a vacuum. It travels through a gas, it travels through a liquid, but it travels best through a solid. And so in your home, the parts of the buildings that convey the sound are things like the joists, the windows in particular, very thin, and you'd like really to try and improve that aspect of a home. And this is what I'm doing with this demonstration here. I call it my Concord box. Would you like to come and help me with this? What's your name?
Charles.
Hello, Charles. Come round. And if you just stand there, what we're going to do now, you can see what's in this big cabinet here. It's Concord taking off, isn't it? Yeah. And what I want you to do is just switch on by turning that up, and we'll listen to the noise of Concord taking off. That's it. If you just turn it, twist it round, switch it on. That's it. So I'm noisy. Now let's put it back down together. It's very effective, isn't it, in cutting out that sound. Thank you very much. So what we've done there is to use double glazing to prevent the sound coming through. 2 sheets of glass, and there's an optimum thickness as well because double glazing isn't just a question of just putting any two pieces of glass together. You must get the geometry right. Now, clearly, if you've got some double glazing, it does prevent sound coming in very effectively, but it also prevents heat loss as well. And that's what I'm trying to indicate with this demo that I have behind me here. I want you to pretend that inside here is your living room. And what I have inside is a large electric fire, which is giving off lots of thermal energy. And that fire has been on for quite some time. These panes, they look the same, but they're all very different. This is a very standard pane, just a single pane of glass. The center one here is a double glazed pane, not very dissimilar from the Concorde experiment you've just seen. And then here we have a special double glazed pane. This has a special reflective coating on it that reflects the infrared radiation back into the inside of the house. Using these three radiometers here, we're going to measure the temperature on the surface of those glass panes. And what we should find is that the simple pane here is at quite a high temperature because energy will have been lost from inside the home and it's going to be lost to the outside. But hopefully what we'll find is that this specially tailored piece of glass here will be much more effective in keeping in the thermal radiation. So let's now look on the monitor here to see just what the temperatures are. The normal pane of glass, which you see here, has a temperature of 28 degrees, significantly above the outside temperature. The double glazed one is lower, it's about 23.2, so that's quite effective in cutting the heat. But the double glazed one with the special coating, as you can see, is down to about 22 degrees, very, very close to the temperature in this room here. And so this just shows that you can modify the properties of the glass to suit the ambient. I want to show you now the spectrum due to solar radiation. On the scale along here, I've shown wavelength in micrometers. This end of the spectrum is the ultraviolet part of the spectrum that gives you sunburn. This is the visible part of the spectrum. And beyond where I've shown the dotted line, you have the infrared part of the spectrum. Hot bodies like you and me, thermal radiators, will emit well beyond that part of the wavelength scale as well. This is intensity that I've shown on the vertical axis. Now let's see what the spectrum looks like for sunlight. This is after it's passed through the ozone layer and so on. You can see that it's more or less divided equally between the UV and the visible on the one hand, and infrared radiation on the other. In your typical British home in a nice cold climate, the sun brightly shining outside, you want to get as much daylight in through your window as possible. But what tends to happen if you just have a normal window there is that most of the heat energy escapes through that window, and energy costs money. So what you want to do is to try and minimize this and avoid that heat energy going out. So you'd like to see it kept within the room. You can do that using special glass in your window pane. And the spectrum of that special glass I've shown on this view graph here. What you want is a piece of glass like this that allows virtually all the daylight to come in, the visible part of the spectrum to be transmitted, but you want virtually none of the infrared to pass through, and therefore in this way you get the benefit of daylight, but the heat energy generated within the home isn't allowed to escape. I have a couple of experiments related to this slide here that I now want to show you. The first one is not very scientific, but it's seasonal and it's good fun, and it mentions chocolate. You can see here that we've strung up a couple of Father Christmases. It looks a bit like a scaffold, doesn't it? We're illuminating them at exactly the same time. But there's a very big difference between these sets of projector lights. One of the sets is perfectly normal. And what that means is it's giving off a lot of infrared radiation, a lot of heat energy. On the other hand, the other isn't. There's a special coating on that projector bulb that is keeping the infrared radiation away from Father Christmas. Now, I'm not going to tell you which one is which. They are very, very different, though, these bulbs. But as you can see, the Father Christmases are positioned in just the same way. It takes a couple of minutes for this experiment to have any genuine effect. And in the meantime, I want to show you my other experiment to do with infrared. I have here a piece of glass that has exactly the spectrum that I showed in the previous slide. As you can see, it's transparent. It's letting in most of the visible radiation. But what I want to measure is how much of the infrared it transmits. And so what I'm going to do is to use this light source here and this radiometer. Now I'm going to put this beam, this filter, into the beam. You can see how effective it is in cutting down the infrared radiation. So it's using a pane of glass like this. You get all the benefit, all the daylight comes in. On the other hand, that heat energy that you've generated, that you've paid for, can get out with great difficulty. It really is a very, very good filter in that sense. This filter, on the other hand, is rather different. As you can see, it's more or less opaque. It's the sort of glass that you would use in a hot climate, where you want to regulate the amount of sunlight coming in. You want to dampen some of that sunlight. You want to really minimize that glare. On the other hand, you also want to make sure that the infrared energy escapes easily from your home as well. So this is a quite different filter to the one before. As you can see, it's quite effective. It transmits most of the infrared parts of the spectrum, but as you have noticed, it doesn't transmit much of the visible. Now I can see things happening over here. Now look at that poor old Father Christmas over there. Those are the bulbs that are just the average normal bulb. Whereas these bulbs here are the ones that you'd find, let's say, in a supermarket, in the fridge area, because again, you don't want to heat up the food in a fridge. So these have been specially designed, and there's Father Christmas really making a mess of himself, isn't he? We've shown now how you can make glass where you can regulate the amount of infrared and visible light being transmitted through. We can also make conducting glass. And you might say, well, why on earth should you want to make glass conducting? Because metals conduct. Well, the reason is very, very important. If you have, let's say, a computer screen with some information on it, it is possible these days, with a special detector van about 300 meters away, to read exactly what the information is on that screen. We call it electronic eavesdropping. And that could be very serious, because more and more information is being put onto computer screens. The reason that conducting glass is so effective is that it effectively cuts out the radio frequency part of the spectrum. If you have a sheet of glass where the resistance is about 2 ohms per square, it reduces to 1/100th the intensity of that radio frequency radiation. It's also very important if you're working near places where there are large transmitters and so on. You might want to protect your equipment from interference. I have here a demonstration to prove just what I've said. Here is a liquid crystal television. I'll be saying much more about this particular television in a later lecture. It's a miniature television, and what we're looking at there is a picture of the street outside, Albemarle Street. What I'm going to do now is to take this glass box, this is just an ordinary glass box, and I'm going to put it over the television. And you'll see the picture of Albemarle Street is still there. Nothing has happened. And that's because ordinary glass transmits radio frequencies with no trouble at all. But this glass has been specially coated. In the process, we use a magnetron to sputter a special conductor onto the surface of the glass. You can still see through the glass, of course, but you watch now what happens when I put it on the surface. Well, it's a poorer picture, certainly. In front of me, I have another example of a sheet of glass that has been coated with a conductor. If you were a burglar breaking into a house, you break that window. What I'm going to do now is simply scribe it with this pen here. And let's see what happens when I scribe it. You see, I've set off the alarm, because in scratching the surface of that glass, I've changed the resistance, and that has been detected in this electronic box here. Now that brings me conveniently to the last topic of my lecture today, which is security. And let us pause for a second while I tell you the story of the policeman who went to night classes to learn chemistry. And do you know what they give to a policeman who goes to night classes in the local technical college to read chemistry? They give him copper nitrate. Now that's the light side of security. There's a very, very serious side to security. In 1987, there were 1 million burglaries or more in this country. The number had doubled just in the last 15 years. Despite all the extra sophistication that the police can bring to bear to try and apprehend these burglars, only about 10% of the material that is stolen is actually recovered. People have for many, many, many years been concerned about protecting their goods and their lives as well. King Henry VIII had a special lock. You'll find it in the Victorian Albert Museum. It's about a foot long, and he carried it with him wherever he went, or at least his servants did, and they would fit it to his bedchamber door to make sure that he was safe on a night time. The biggest lock in Britain is about 23 miles long, and it's called Loch Lomond. On my right here, you see an example of a very, very early lock. In fact, this is a replica of an old Egyptian lock. This is the key. It looks more like a comb or a weapon, doesn't it? But by putting these metal prongs into the right slots here, you can unlock the bolt. See? Very, very, very simple. Here I have another very, very similar lock. This one was used to guard the pharaohs. These also, because these are from the Faroe Islands. Very, very similar principle, with just these tiny wooden pegs here, so that with a key, you can put it in and lock the bolt. This is the principle of the Yale key. Yale, Linus Yale Jr., invented his key in 1850. But really it's the same principle as this, it's just made out of metal. I have here a cross-section of a Yale lock and a key. Same principle as those early wooden locks, except now we have brass tumblers here. And if I push in the key very slowly, you'll see these tumblers moving. And the clever thing is that the little cut that is in here, in each of these, lines up. And so this means that the cylinder will rotate, and this unlocks the door. Let me try and do that again for you. I'll just push in the key slowly. And you see all these notches here? They've all lined up beautifully. The principle of the Yale key is very, very similar to those other keys. In this case, though, you've got 5 notches, and they can be machined to 8 different depths. And that gives you 32,768 combinations. And that's the principle of the Yale key. There were other quite important people who got involved in locks in the past century or so. In particular, an American called Hobbs invented a lock that was programmable. But nevertheless, it had a bulky mechanical key. Modern science and engineering has led us to electronic keys. There's been a revolution in the last 10 years or so in access to buildings. No longer do people have to carry bulky keys, mechanical keys along with them. They can have some other method of identification. The first method I want to discuss with you is using smart cards. And if I could have a couple of assistants, please. Would you two gentlemen like to come down and help me? Thank you. What I would like you to do is to put this smart card, and you can see it's got a magnetic strip on it, into this special slot here, and just move it downwards like that. And let's see if you can open the door. Now, why don't you try and do the same thing? No, the magnetic strip needs to be on that side. That's it. You see, you've opened. You have to open it very quickly, obviously, after. That's it. So both of you have, if you can hold on to that key, both of you have had access to that door. On the back here, you do have this magnetic strip. But what I'm going to try and do now is to damage the information that's written under that strip. And so, if you hold that one there, I'll put the magnet now across like that, and I'll do the same with yours. Now, why don't you this time try again? See, I've wiped the information clean, so I'm afraid that card's no use anymore, and I must ask you to go back to your seat. You haven't tried, have you? Why don't you try? Right, try again. Ah, it's worked, you see. Your magnetic strip is different to the other one. This has got an indelible magnetic print on, and no matter how hard I try with this magnet, I can't erase it. So this is a very, very different strip, and we call this watermark. And I want to try and explain now with the film how this watermark principle works. Thank you for helping me. That black strip that you saw contains magnetic particles. And unless you do something special to them, they'll be aligned in a very random way. On the other hand, if you apply a magnetic field, and this blue line indicates the magnetic field, those iron particles will align in a particular direction, just as I've shown there. If now the magnetic field is pointing at right angles to this, these particles will now align in the other direction, just as I've shown here. Let's imagine now that you have a belt of magnetic materials moving along It's wet, it hasn't been fixed yet. And you have an AC field applied, so you're producing an alternating magnetic field. What you'll end up with if you do that is a pattern. And this pattern will comprise particles pointing this way and that way. And that'll be a unique pattern that you can fix. It'll be unique to that one particular card. Very, very different to the conventional cards. And that's the type of magnetic strip that we have in here, and you can see it on the screen there. One of the troubles with this kind of card, even though it's used for 80% of the cases where electronic control is needed, is that it's very easy for me to give this card to somebody else and for them to use it to get in. So it's not totally secure. It would be far, far better if the access control depended on one of my human characteristics. And what better than a thumbprint or a fingerprint? Fingerprints have been used for long, long time by the police to apprehend criminals and so on. A thumbprint like this is unique to an individual. What I have behind me here is a thumbprint detector. Before the program started, we fed the thumbprints of a couple of members of the audience here into this machine here. And I'd like the two of you now to come up. Your name is?
Alex.
Alex?
Joe.
Alex and Joe. They were given a special code. What was your code, Alex?
4321.
4321. Will you put in 4321 into the machine and put your print in, and let's see if it opens the door. There we are. You see, you've opened the door. It's remembered your code, and it's remembered your thumbprint. Now, Joe, would you like to do the same? What was your code?
8888.
8888, right? You dial that in. Right, that's good, isn't it? Well, if you go back to your seats now, I'll see if I can prove that the system doesn't work for everybody. Would you like to help? What's your name?
Charles.
Charles. Come on, Charles. Now, you remember Joe's code was 8888, wasn't it? Now, why don't you try and beat the system, use that code, and try and get into my house? No, I'm sorry. Do you want to try again? No, sorry, mate. Awfully sorry. Thanks for trying. Now let me have another volunteer to help me. Would you like to help? What's your name?
Daniel.
Come on, Daniel. Now, Daniel, you actually were given the thumbprint test as well, so you could, in principle, use that machine, couldn't you?
Yes.
And let me give you my special watermark card as well.
Thank you.
Okay? Now, what I'm also going to give you, I'm going to be very, very generous. It is the season of goodwill. Let me give you a couple of gifts. And a couple more as well. Right? Can you manage them? Right? Now, would you like to open the door, please?
I can put the card in my key.
It's difficult, isn't it? And now we've found a weakness of this thumbprint system. It really isn't going to be used very easily. Why not take those away? They're empty, unfortunately, but thank you for helping. So we've found now a limitation of the fingerprint technique. The fingerprint technique is just one of a range of techniques we call biometric techniques, where you're making use of a characteristic of the human. What better then than the voice? The voice is something that, again, is unique to an individual. And what I want to show you now is a system, a voice recognition system, which has been developed at the University of Edinburgh. We've asked the help of some famous people with this demonstration. The first one I want to mention is the Prime Minister, Mrs. Thatcher. Now, how many of you know, I wonder, what the maiden name of Mrs. Thatcher was? Do you know what it was? Roberts. Isn't that a coincidence? She was Margaret Roberts, and like me, she went to Oxford University. Margaret Thatcher, some years ago, was asked a question. She was asked, would there ever be a woman Prime Minister in her lifetime? And this was her reply.
In theory, but not in practice. I don't think there'll be a woman Prime Minister in my lifetime, as far as I can see.
Now, that just goes to prove that even Prime Ministers can be wrong. Now, let's repeat that sentence.
In theory, but not in practice. I don't think there'll be a woman Prime Minister in my lifetime, as far as I can see.
Well, that's surprisingly similar, isn't it? But that isn't Margaret Thatcher, or Margaret Roberts speaking. That is the famous impersonator, Janet Brown. Janet Brown has agreed also to help us on this programme. And what I have in front of me here is the voice print, or the spectrogram, of both Janet Brown and Mrs. Thatcher. So here we have the genuine Prime Minister's spectrogram. And here I've got the imposter, Janet Brown. The words that we've highlighted here are the part of the sentence where they say Prime Minister. So this is Prime Minister. When you look at those spectrograms, there's some very, very similar features. So as Janet Brown said Prime, very, very similar pattern to Margaret Thatcher. So that the frequency scale that was used, the vocal tract, was giving just the right frequencies. Also, as the word the minister, the end of the two words was said, again, very, very similar features, like this one here and this one here. Janet Brown had done extremely well in trying to mimic the voice of the Prime Minister. And obviously, when she dresses up like her as well and has all the mannerisms, it really is difficult to distinguish them. But the important thing is, can this voice recognition system recognize the difference? We've already fed the voice, Prime Minister, Margaret Thatcher's voice, into that machine. And what we're going to do now is to play back that voice, and we'll see whether the instrument recognizes her.
Prime Minister.
Except the door unlatches. Now, the test, the real test. Can Janet Brown, saying Prime Minister, open this door?
Prime Minister.
It's been rejected. And that really shows you the sophistication of this equipment here. It really can distinguish those minor differences in the spectrogram, and now we really have an excellent way of access control, very convenient to use because you carry your voice with you wherever you go, don't you? And you can't lose it unless you have a heavy cold. Well, in this lecture, I hope I've unlocked a few secrets for you, and I hope I haven't been too great a pain. Tomorrow's lecture is going to be about the future of television. Do you know that the average British viewer spends 28 hours in front of the box every week? I'm hoping that one of those hours will be watching my next program called Electronics for Pleasure. Thank you very much for your attention.